Your classifier can be accurate and still dangerously overconfident. I'll use label smoothing in PyTorch to tame confidence without rewriting the model. This is the pattern you'll be able to implement by the end, which trains with label smoothing and returns calibrated probabilities with a quick confidence error. I'm Professor Pi, teaching AI foundations with simple Python. Imagine you built a classifier that gets high accuracy on validation. It looks great until it confidently says wrong answers with 99% probability. That mismatch between probability and reality is calibration failure. In practice, it matters when decisions depend on probability, like triage, alerts, or downstream models that use those scores. Better calibrated probabilities make systems safer and more reliable. At its core, label smoothing says, do not force the model to predict a single class with absolute certainty. So instead of a hard one-hot target, we spread a little probability mass to other classes. That simple change nudges the model away from extreme logics and toward probabilities that better match observed accuracy. We will build a tiny linear classifier on a toy 3 cluster problem. Train it normally, then train it again with label smoothing, and finally compare confidence versus accuracy. The code is short. The ideas are the same you would use in a larger project. Now we'll turn raw scores into probabilities so you can see overconfidence. This snippet converts raw class scores into probabilities using PyTorch to make overconfidence visible. We start with logits, which are unnormalized scores for 3 classes. The softmax function in PyTorch's functional module transforms logits into a probability distribution that sums to 1. We then take the maximum of these probabilities to represent how confident the model would be in its top prediction. Because one logit is much larger than the others, softmax concentrates most probability mass on that class. A high printed confidence signals a peaky, overconfident prediction that may be brittle. Next, we will compare the training loss with and without smoothing to see how the objective changes. This example computes loss in PyTorch with and without label smoothing to show how it discourages overconfidence. We keep the same logits and define y as the true class index. The cross-entropy function in PyTorch's functional module applies softmax internally and measures how well logits match the target. With label smoothing set to 0, we get the usual hard label loss. And with label smoothing set to 0.1, the target becomes a soft distribution. That softened target spreads some mass to non-true classes, so the loss penalizes assigning too little probability to those classes. Increasing label smoothing raises this penalty and encourages less peaky predictions. Decreasing it moves back toward hard labels. A larger smoothed loss here indicates that our very confident logits get explicitly regularized. Now, we'll train a minimal model on a tiny dataset and watch how confident it becomes. This code trains a small linear classifier in PyTorch using hard labels and reports average confidence. We build a toy dataset X with 3 simple clusters and labels Y. A minimal model, a sequential model with a single linear layer, maps 2-dimensional inputs to 3 class logits. Using the SGD optimizer, we run a short training loop, minimizing the cross-entropy loss to fit the data. After training, we convert final logits to probabilities with softmax and take the maximum probability per example, then average those maxima to summarize confidence. More epochs or a higher learning rate usually push confidence up faster, while fewer updates keep it lower. A very high average suggests the model learned extreme, possibly overconfident predictions. Next, we will train the same model but use label smoothing to regularize predictions. This snippet repeats training in PyTorch, but enables label smoothing of 0.1 to reduce overconfidence. We reinitialize an identical linear model and optimize it on the same x and y, so the comparison is fair. The cross-entropy function now uses softened targets, distributing some probability mass to non-true classes, which acts as a regularizer against peaky logits. The training loop and optimizer remain unchanged, so your pipeline stays simple. After training, we again compute the mean of per-sample maximum probabilities to summarize confidence. Increasing the smoothing value pushes probabilities to be less extreme, while decreasing it narrows the effect. A lower printed average confidence after smoothing indicates predictions are less extreme and typically better calibrated. Finally, we will measure calibration directly by comparing confidence and accuracy on a held-out set. This example estimates calibration by comparing confidence and accuracy on a held-out set using PyTorch. We create xt and yt as simple test points positioned near the training clusters. With the No Gradient Context Manager, the trained model makes predictions, and softmax converts logits into probabilities. The call to get the maximum returns both the highest class probability per example and its predicted label. We compute accuracy against yt, then subtract accuracy from the mean confidence to form an overconfidence gap. Smaller gaps imply predicted probabilities better reflect reality. Larger gaps suggest unreliable confidence. A small printed gap indicates the smoothed model's probabilities are closer to being well calibrated. To map this toy example to a real system, replace the 3 clusters with your labeled dataset, keep the same training loop and smoothing value as a baseline, and evaluate confidence minus accuracy per slice or class to find where calibration fails. Recap. Label smoothing softens targets to discourage extreme probabilities. Use it when you need better calibrated probabilities, especially for decision-making and downstream systems. One caveat: smoothing slightly changes the learned decision boundary and may reduce top 1 accuracy in exchange for better probability quality. Next step: tune the label smoothing parameter. For example, try values like 0.05, 0.1, and 0.2, and measure the overconfidence gap and accuracy trade-off to find the sweet spot for your problem. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.